After making the netcode for Ballistic, I became really curious about the underlying systems that went into the framework we had used, Photon Fusion. I understood a lot of it at a high level, but I wanted to get a good grasp on it by creating it myself. After graduating college this past year, I suddenly found myself with a lot of unemployed free time, so I decided to use that to go as deep as I could into understanding everything I could about multiplayer. This video is going to be part tutorial about networking techniques and part documentary about that process. On the whole, this is going to be a complete overview of what I've learned over the past year of studying multiplayer, from basic network programming to complex state management to backend architecture. This is everything multiplayer. The first step is to create a framework, like Photon Fusion, that I can build off of. I'm going to call it OwlTree and build it with C# since I intend to bring it into Unity. It, as well as all the code that I show in this video, is up on GitHub for you to look at. Now, the main feature that really awed me in Fusion was remote procedure calls, or RPCs for short. An RPC allows one computer to invoke a function and have that function execute on another computer. I know now that this is pretty standard in a lot of networking frameworks, but the idea that you can call a function on another computer was like magic to me when I first learned about it. So RPCs are going to be the main goal I want to achieve in OwlTree. But before that, we have to get two computers talking to each other. This is done with sockets, which gives us an interface to send and receive data from specific endpoints. These are identified by an IP address which differentiates computers, and a port number of which there are many to allow multiple sockets handling network traffic on the same computer at the same time. There are two protocols I'll be using with these sockets, TCP and UDP. To set up a TCP connection, the server will first bind to its local endpoint to start listening for clients to connect. The socket we make here isn't what's used to send and receive our own data, but is instead a waiting list for connection requests. Once clients are connected, they'll be given their own socket. Since the server will be dealing with multiple sockets, I'll use select to filter for ones that have data waiting on them. If that first waiting list socket is included, that means a new client is trying to connect. And otherwise it means that an already connected client has sent something. On the client, I need to connect to the server's endpoint. Unlike the server, the socket will automatically bind itself to an available local port, which, by the way, we can do on our own by setting the port number to 0. Once the server has accepted the client's connection, it can send data. I clipped these two classes short for presentation, but at this point, their send and receive methods are basically identical. The only difference is that the server would use one of the sockets from the client's list to send data to someone, and not the waiting list socket. TCP sockets do a lot of work for us. They have the concept of a connection, which means the sockets on either computer are specifically dedicated to only sending data to each other, and they'll regularly check to make sure that they can still reach each other. TCP will number packets and do everything it can to make sure things arrive in order, and nothing gets dropped. This is very expensive though, so TCP is considered reliable but slow. UDP, on the other hand, is much more simple. For both the server and the client, all they have to do is bind to their local endpoints. Then, to send data, you just specify the remote endpoint you'll be sending this data to. When you receive data, you'll also get the endpoint that sent it. As you can probably tell, UDP allows you to send and receive data from any remote endpoint. This is because UDP doesn't have the concept of a connection. It doesn't do any of the management TCP does, which means packets can be dropped or received out of order, so it's considered fast but unreliable. Despite this, UDP is the preferred protocol for games since internet connections have become so reliable now, packet drop is less of an issue. And the cost and speed of TCP is really not preferable for games. The standard now is another protocol built on top of UDP called Reliable UDP, or just RUDP. In practice, RUDP is basically just remaking TCP, but ignoring parts of the protocol that make it slow, particularly exponential backoff. The idea is that with each failed send attempt, the sender should wait some time, assuming the internet connection needs to recover. With each failed send, this time doubles. RUDP can just skip this step and perform resends immediately. Since the underlying socket will still be UDP, we can still share it between multiple clients and handle the individual connections through the program. Each client is associated with a remote endpoint, which we can use to send data back. Whenever the client is accepted to the server, its endpoint will be added to the RUDP socket as a registered endpoint. The socket will then start ordering the packets it receives and tracking which ones are missing. Resend requests will be sent for missing packets, and delivery will be prevented until missing packets arrive or they expire, which will just be some multiple of the client's measured latency. Similarly, sent packets will be temporarily stored in case someone makes a resend request to us. So that the socket can receive everything waiting on the line and sort the received packets, I chose to add a second step to actually get the packets from the queue. This is just run in a loop to read everything until the queue is empty or you hit a missing packet. Despite having RUDP, TCP is still useful. Since TCP is such a ubiquitous protocol, a lot of our internet infrastructure is built to support the reliability and performance of TCP. No matter what, TCP will probably always be more reliable than anything we can make at the program level. Because of this, supercritical data like notifying other players someone else joined or left, or that the level should be reset for the next game, I still prefer to send with TCP. The setup I'm going to use will have the server form a TCP connection with each client, and have a single UDP socket that everyone shares, which will be using the RUDP I built. Clients then have corresponding TCP and RUDP sockets of their own. Using the socket send and receive methods, I can send data between computers, but I need to decide how that data will be structured. When sending data, it's represented purely as an array of bytes called a packet. For each packet sent, I dedicate some bytes at the front to the header, which will contain a bunch of metadata such as version numbers, a timestamp, and the packet number, which for now is only used by the RUDP socket. The most important part for now, though, is the packet length. After the header is the actual data, which will be split into individual messages. Each message will be given a length at the start. That way, a received packet can split into a sequence of the messages it contains. I'll make a separate packet class that wraps this functionality. I can use spans to pass around a limited range of a packet, which will make encoding and decoding messages easier and reduce garbage collection since spans reference the same byte array, so I don't have to make a bunch of copies. Then I can produce a complete packet from that object and similarly feed raw data into it. Reading data from a socket requires providing a buffer to fill. This buffer is a fixed size, so what happens if the packet is longer than the buffer? I used two different solutions for this. The first was for my TCP packets. I can use the packet length from the header to continue reading data and adding to the packet until the full length has been reached. Since TCP is a data stream, the next packet will be stacked right next to the previous one. This means the buffer can contain data from two different packets. I can tell that this is the case if the previous packet has been completely read, but the data length returned by socket.receive shows that there's still more bytes in the buffer. In that case, I can start reading a new packet from wherever the last one left off. The other approach I used for my UDP packets. Instead of sending one big packet, which UDP isn't really meant for, I instead split big packets into smaller ones. This is called packet fragmentation, kind of. I walk the packet by message so that there's never partial data, and stop once the next message is too big to fit in the buffer. That's then sent as a packet, and the remaining messages are shifted down to repeat the process until everything has been sent. I'll also add this packet splitting as a failsafe on my TCP packets to avoid excessively large packets. I know how collections of messages are sent and structured. Now I need to decide how individual messages are encoded and decoded from raw bytes they're sent as. I'm glad I chose to focus on RPCs, because I can lean on this to guide how I'll do this. The main data that needs to be sent for an RPC are its arguments, but of course each one will have a different set of them. To differentiate between RPCs, the first piece of data in a message will be an RPC ID, which will be a unique integer. The value of this will determine how the rest of the data in the message will be treated. I'm going to reserve the first few IDs for special messages. the very first of which will be for assigning unique number IDs to clients when they connect. This will be the way players are differentiated from each other and can refer to one another. It'll just be an incrementing 32-bit int that the server will keep track of. It'll send connected and disconnected RPCs to clients so that they can keep an up-to-date list of all the other clients in the session. So I can try out what I've made so far by running a server on AWS and get a random client connected that I'm not running. Looks like I'm going to need to add some security features. To prevent random connections, I added an app ID and a session ID to differentiate clients from different apps and different sessions of that app. The way it works is before clients try to make a TCP connection, they'll send the IDs through UDP. The server will then compare that with the IDs it has, and if they match, the client's IP will be added to a waiting list, and the server will send a message back telling the client they're good to connect. That way, only IPs that are on the waiting list can be allowed to make a TCP connection, and be given a client ID. With that client ID, I'll also send them a random number that I'll call their hash. This isn't shared with any other client and is used to superficially verify a packet is from the right client. Not very secure, but that's a problem for future me to solve. Once a client is connected, if clients send too many malformed packets, they'll be kicked from the session. This doesn't exactly completely protect the server, but it'll at least make it so it requires a bit more sophistication to spoof a real client. With this, I'm almost ready to build RPCs, but before I do that, I want to take a detour to talk about the two topologies you'll use for a multiplayer game. The first is server authoritative, where players connect to a server which manages the game and acts as the authority, which is the computer that gets to tell everyone else what is and isn't true. And relayed peer-to-peer, where players connect to a relay server whose job is purely to pass data between players, and one of the players acts as the authority instead, affectionately called the host. Server authoritative is needed for cheater prevention since the authority of the game is a computer you control, and since that computer will likely be hosted in a server room somewhere, its internet connection is going to be pretty reliable, but this as a whole is more expensive. Relayed peer-to-peer is cheaper because all the server has to do is pass data back and forth, which takes less memory and processing power. However, having players act as the authority opens up more potential for cheating, and the general latency of the game will depend on the host's internet speed and computer performance. Considering the general trend in indie games for co-op and party games where latency can mostly be compensated for and cheating isn't that big of an issue, I'm going to say there's like an 8 out of 10 chance you should be using relayed peer-to-peer for the game you're making. Both of these I want to support with OwlTree. The server will largely follow the same setup I've shown so far, tracking clients and receiving messages. A relay, on the other hand, won't necessarily be receiving any messages itself. Instead, it'll be taking the messages it gets and repackaging them to be sent out to everyone else. In other words, relaying them. One architecture I'm leaving out is actual peer-to-peer, where there's no server involved at all. This is only something you should really consider if you're looking at making something like local Wi-Fi multiplayer like what's offered in Bedrock Minecraft or some sort of LAN setup. True peer-to-peer for games is considered out of date now since it's a lot harder to make a direct connection to someone's private computer as opposed to a public server. And creating direct connections between random computers generally isn't a good idea for security. Alright, back to RPCs. Now that I had sending and receiving data figured out, the next step was making something to call RPCs on. Since C# is an object-oriented language, procedures are attached to objects, so I need to have the same object exist at the same time for all connections and be able to reference it. To do this, I made 3 things. Network objects, which will be the type of object that can be spawned across clients. Network IDs, which are just like client IDs, but will be used to uniquely identify network objects. And a network spawner, which will be used to create and destroy objects across all clients. I made it so that only the authority is allowed to spawn and despawn objects. That will prevent things like 2 clients spawning objects with the same network ID. I made 2 more RPC IDs, spawn and despawn, and then used a source generator, which is essentially C#'s ComTime feature to collect all the network object types for your project and assign them IDs. That way the authority can say spawn object type 3 with ID 2, and clients will know that means a player object with the network ID of 2, for example. Then each network object can be referenced by its network ID, so I can say call RPC number 5 on network object 3. The last thing I want is a way to encode arguments. The bit converter library is useful for converting primitives, but I want to add a way to make your own encodable types. So I made the iEncodable interface, which will make it so that you can specify how an argument is encoded and decoded, which means I can make a bunch of new types that can be used as RPC arguments, and also use the source generator to verify if an argument is valid, since that's a feature they have. Okay, with that I have everything I need to start making the actual RPC feature. I decided to copy the look from Fusion. RPCs are marked using an attribute, and the attribute arguments are used to define metadata about the RPC, like who's allowed to call it, whether or not the RPC should also run locally, and whether it should be sent via TCP or UDP. I also made special client ID arguments. One allows the caller to specify a singular client that will receive the RPC as opposed to sending it to everyone in the session. The other exposes the client ID of the caller. Each RPC call is a message, which will be added to the outgoing packet. It'll be encoded first with the RPC ID, then the client IDs for the caller and callee, then the network ID of the object it was called on. The challenge I needed to figure out now was how I can inject the code into RPCs that made it so that they call encoding logic instead of just running the method like normal. The solution I settled on was to create proxies for each network object, and those proxies override RPCs. To make those proxies, I used another source generator. It collects all the RPCs in the project, assigns them their IDs, and hard codes their encoding schemes for their parameters. So the full lifetime of an RPC goes like this. When you call it, you're actually calling a proxy, which will pass the arguments to encoder. The encoder will then create a byte array, encode the arguments into it, and pass it to the send queue to be added to the outgoing packet. Once that packet is received, it's split into the individual RPC messages and processed one by one. First, the RPC ID is decoded to get the hard-coded parameter types created by the source generator, so that the arguments can be decoded and placed in a receive queue. The decoded network ID is used to find the object the RPC was called on. Then this is all passed to a source-generated invoker, which will call the actual RPC method and bypass the proxy. All of this is then encapsulated in a class I called connection, which contains the whole OwlTree interface. So, the full workflow shaped up to be: create a new connection with a specific role, server connections will open up TCP and UDP sockets, and client connections will send connection requests. The authority spawns new network objects, which contain RPCs for sending data. Called RPCs are added to an outgoing send queue. That queue gets consumed when you call send on the connection, which builds and sends packets. The receiving connections will then read everything on their sockets when you call receive. This will take the packets that are received and split them into individual messages, and then add the decoded RPC to an incoming receive queue. The RPC is finally run on the receiver by calling execute queue, which consumes the read queue, passing the decoded arguments to the specific RPC on the specific network object it was invoked on. The reason the core loop is split into receive, execute queue, send is because I can then make this multi-threaded, where receive and send are looping in a separate thread, and the receive and send queues are thread-safe message queues. This way, the core network management can be handled asynchronously, and execute queue can be run as part of the main simulation loop. This isn't everything I made for OwlTree, like how I rebuilt the entire thing like 3 times, but this is a good enough overview of the essential components to give a good foundation for what's coming next. The main thing that I was really proud of at this point was that I had actually made a decently robust RPC system. Even though this all might look complicated, this is still missing a lot of features that modern multiplayer frameworks provide, which we'll be getting to. But still, now that I have this built, I can go into the higher level techniques used to create a multiplayer video game. previous part went into a lot of specifics, although anyone looking to make a game shouldn't be making their own framework, and should instead use an existing option. While I'm going to continue using OwlTree for the rest of this video, I'm going to make everything I show roughly applicable across any setup. It doesn't matter what tools you're using, the ideas still work the same. Now I can finally move into an engine, and I need to make OwlTree work with Unity now. I'll make a wrapper component for the connection class, and since instantiating prefabs isn't the same as creating new objects, I'll make a separate prefab spawner that manages network game objects by spawning prefabs with assigned IDs. Essentially the same system as type IDs to network IDs, but with prefabs and game objects. And then I also need to get the source generator to work in Unity, which was a pain. There's one page of documentation on it, and it's single YouTube video. Since network objects are their own type, components will have to spawn them separately, and use them like detached netcode objects. Which isn't the end of the world. Architecturally, one of the biggest pain points during Ballistic was how netcode and game logic were coupled together, which makes it really difficult to test as the project grows. Since netcode is generally reliant on the networked environment setup, it requires a bunch of overhead to do simple tests. Basically the typical complaints you'd see with singletons. As an example, I'll make a network state machine. The state machine itself is pretty typical. States can have a super and substate, and are swapped between. Each state has update callbacks that run game logic, and are typically organized in layers, where states from one layer don't move to another layer. For example, with a player controller, you'll either be moving or idle, but never both. So those two states would go on their own layer. Similarly, you'll either be grounded or airborne, so those two get their own layer as well, along with a jump state to transition from grounded to airborne. I usually call them layers because I find people get it better, but the actual name for this is a hierarchical finite state machine. If you aren't familiar, you can check out this tutorial. The state machine can then be given to a player script that calls its update methods. To make this networked, I'll make a separate network object type and give it all of the possible states, which it will assign IDs to. That way I can say swap the state at index 0 to state number 3, and the client will know to swap grounded with airborne. The netcode on the authority will subscribe to an event on the state machine that's invoked whenever states are swapped, and that will run an RPC to send that state change to the clients. The last piece is just a network transform that will continuously send position and rotation updates. And with that, we have a networked player controller state machine that can be decoupled from the netcode. Off of this, we can explore the problems you have to solve when making multiplayer. There are three main ones you'll always have to contend with: bandwidth, packet drop, and latency. Bandwidth is the amount of data that's being sent and received. We always want to minimize this, since sending too much data can result in throttling, where the amount of data allowed to pass through the player's network is intentionally limited. This will worsen the other two problems, packet drop and latency. Most server providers also bill you based on the amount of bandwidth your game uses, so sending excessive amounts of data will literally cost you. To measure bandwidth, I added steps before sending and after receiving packets to record their byte length. I like to measure two things: kilobytes per second and megabytes per hour. Kilobytes per second is useful for determining what parts of your game are real bandwidth hogs. A good test is to put 100 of something in a scene and see how much bandwidth they use. Megabytes per hour is useful for figuring out total data usage. I like to frame this in terms of what the typical play session is. If players typically play for 30 minutes a day, then they'll be using about 50 megabytes for each session. Given so many daily active users, there'll be this much data transferred each month. Can I afford this, or is this under my limit? For a video game, my old professor described under 10 kilobytes per second as literal noise. Just doing a simple Google search, the average usage seems to be around 10 to 20, with more competitive games going around 20 to 30. I'd say if you're able to stay under 10 kilobytes per second, then you don't have anything to worry about. And of course, this will depend on what you're making. A turn-based game should take borderline nothing to run. The most obvious way to reduce bandwidth is with compression. I can use one of those header flags to mark a packet as being compressed, and then use Huffman encoding to compress the actual data. This got me about a 40% reduction in packet size, which is alright. There are more sophisticated improvements that can be made on top of Huffman, particularly expanding tokens to include words and not just singular bytes. But I'm not going to bother with that since there are more interesting approaches. Most frameworks will be doing this compression at the packet level for you already. The next way is to just represent data with fewer bytes. For example, a single rotation axis would normally be represented with a float, but you could instead split the 360 degrees into 256 discrete rotations and represent it with a single byte. So a full Euler angle rotation, instead of requiring 12 bytes, only requires 3. This is called quantization. I'd say you should be trying to quantize every value you send. If you have an index you know is never going to exceed 255, use a single byte instead of an int. If you're updating a float that can only be a select few values, assign them IDs and send it as a byte. You'd be surprised by how common it is to be able to replace a larger value with a single byte. For a more specific example, let's say the Y position of your game never exceeds a magnitude of 10 in either direction. Instead of representing it as a full 4-byte float, you can quantize it into a single byte using fixed point representation. 10 will require 4 bits plus 1 for the sign, leaving 3 bits for the decimal. In order to convert this to a byte, we'll first have to bit shift the fraction of the float left by the number of bits we've allocated to the fraction of the quantization, in this case by 3. We can do that by multiplying the float by 2 to the power of 3, or just 8. Then we can convert the float to an integer, chopping off the remaining fraction, and bit masking that into the resulting byte. To decode the float, we just work backwards, pulling the integer out of the byte, then dividing it by 8. This value will have an error from the original since we sacrificed fractional accuracy for fewer bytes. On top of that, if the original exceeds the valid range for this quantization, the replication breaks. This becomes a balancing act since positions will appear noticeably desynced without about a plus or minus 100th error. So you want to give as many bits as you can to the fraction, but that depends on the range of values your game will require. For example, in Ballistic I tried to make positions that only require 4 bytes. The issue was that the range of coordinates I needed to be able to represent were about positive and negative 50 in all 3 axes. If I represented each axis with only 10 bits, 1 bit would go to the sign, 6 bits would be needed for the whole number, leaving only 3 bits for the fraction. That meant a position would step by 1/8 of a unit, way more error than 100th. One piece of advice my professor gave me was that sometimes you shouldn't quantize because it can potentially reduce the effectiveness of compression. I know now though that this is actually wrong. Since compression algorithms are looking for repeating bytes, and reducing the range of possible values you're sending increases the likelihood of repeating bytes, quantization will actually improve compression. Using my own poorly optimized Huffman encoder, I was able to get some 10% better compression out of quantized values, and that's on top of the massive reduction from quantizing already. Even if you don't think you'll be able to quantize values as heavily, you can still use a delta-delta set pattern. Instead of sending whole values for each update, you can send the displacement from the previous update. Since this will probably be fractional, or at least have a smaller magnitude than the whole value, you can dedicate more bits to the fraction until you get an acceptable amount of error. Then the client applies the displacement to their local value. Because there will still be some error, only using deltas will result in the authority and client progressively becoming more and more out of sync. So at regular intervals, a full state update needs to be sent to get the client back on track. Thus the name delta-delta set. The more deltas you send, the smaller your packets will be, but you'll get worse desync. So once again, it's a balancing act. If you do this, there are 2 edge cases you'll need to deal with. If the delta is too big to represent at your quantized scale, then you should just send a full state update. If you're regularly hitting this case, this means your delta quantization is too small, and you'll need to either increase its error or its size. The other edge case is the delta being too small for the quantization. If this happens, then the client will just get a bunch of zeros, and you'll see it teleporting around with each full state update. To avoid this, you only send a delta update when the displacement exceeds the error of your quantization. Opposite to the other case, if this is constantly happening, then you should decrease the error of your quantization, which could also require increasing its size to add more bits to the fraction. While I'm using positions for this example, delta-delta set can be used for more complicated state than you might think. For example, let's say you want to display text as the player types it. Each time they type something, you don't want to send the entire string, just send diffs. Then, when you want to set, hash the full string into an int, and send that with the string's length. If the replication doesn't produce the same hash and have a string that's the same length, only then will it require the full string. This is called a checksum, so in this case you can call it delta delta check. The last major approach to reducing bandwidth, and the most effective, is to just not send anything. This is why turn-based games should take so little bandwidth. The only time anything needs to be sent is when someone is communicating their move. Otherwise, nothing should be going over the line. But in a real-time game, the decision of whether to send or not to send becomes a little more difficult. The first strategy isn't to send less data per se, but to send data less frequently. I mentioned before that my compression had a 40% reduction in packet size. If I increase the time between my network thread iterations, then there will be more messages waiting each time on the send queue. This, in turn, will increase the size of the packets being sent. Since compression is multiplicative, bigger packets mean a greater reduction. As a result, I'll be using less bandwidth without even needing to send less information. The trade-off here is that the receiver will be waiting longer between state updates, effectively artificially increasing latency. As a result, this isn't a great option for fast-paced games where latency trumps bandwidth usage. In a game with a lot of physics objects, at any given time a majority of these are usually not being interacted with and are not moving. When that's the case, there's no point in sending any updates for them at all. If the authority sees that the displacement from the last tick is 0, then it can send a special state update that tells the clients that the object has come to rest, and can stop sending state updates until it moves again. On the client, for as long as that special update was the last one received, it will keep that object locked in place, which is important to prevent that object from rolling off somewhere else now that it's not receiving constant updates. In a similar vein, if objects are far away, such as players on the other side of a battle royale map, there's no reason to be sending you constant updates as if they're right next to you. This is called area of interest. If objects meet certain requirements, you can either include or exclude them, whichever is easier logically, from a client's area of interest, and anything outside will receive updates at a significantly reduced interval, or not at all, which is approaching a different concept called fog of war, where you exclude state updates to things a player shouldn't be able to see. This was originally a way to combat cheating in RTS games, where hackers would lift the fog of war on their maps to reveal the other players who would otherwise be hidden by it. A lot of things can also be inferred or calculated by the client with only a little bit of information. If there's an animated event, such as a train arriving, instead of syncing the position, have the authority send a future timestamp for everyone to start the animation at the same time. Packet loss is when, for one reason or another, a packet simply doesn't get to the recipient. Even though it's becoming less and less of a problem as internet infrastructure becomes more and more reliable, you as a developer can't really prevent it from happening. Anecdotally, we were usually playtesting and showcasing Ballistic in places that had horrible internet connections. Early on, games were constantly desyncing, people were dropping out of games, and it was super laggy. Playing on home Wi-Fi, it worked fine, but to get good playtesting feedback, I needed to make sure the game could handle pretty severe packet drop. So for the sake of making good netcode, you should treat packet loss as a natural condition of networking. You can use a tool called Clumsy to simulate bad network conditions on your computer. I can set packet loss to something ridiculous like 50%, and see what happens to the game. Looking at the state machine, if a swap is lost, then that will cause a desync that we don't want. In this example, it's the difference between being in an idle state but moving. So if there was an actual character, you could imagine that it would just be in an idle pose sliding across the ground. TCP and my RUDP sockets might mitigate this, but I made it so that RUDP will still abandon packets to avoid excessive waits, and even TCP can fail delivery. To deal with this, you need to answer the question, what happens if this message isn't received? For a lot of messages that are received continuously, like positions, dropped updates aren't that big of a deal, since they're presumably going to be replaced in a fraction of a second anyway. So the important part is making it look like nothing was dropped as best you can, which you can do by just lerping between values to make up the missing ones. This is a technique I'll expand more on later, so keep it in mind. For messages that are communicating distinct events, there are two approaches I like to use. The first is for events that happen regularly during gameplay, such as state swaps in a state machine. Much like delta set, the authority can send occasional full states or preferably checksums to verify parity. Clients can also compare state changes to what is known to be valid and request corrections if they detect something off. This can reduce the need to send potentially pretty large verification messages. If clients try to send their own messages that depend on the other player's state, such as damaging them when they're actually invincible, the authority can send a correction update back to the client. The other approach I use for level loading. Since everyone will be sitting in a loading screen, you can take your time verifying delivery. When a new level is being loaded, the authority can send all of the relevant reset data. What scene to load, where to place players, what level enemies should be at, what weather will be, whatever you need. After that, clients will send ready messages back to the authority saying that they're all set up. If any clients didn't say that they're ready, the authority can repeatedly ping them asking for a response. If those clients miss the reset messages, then they'll see the pings from the authority and know to send a re-request to them. If some clients still aren't ready after some arbitrary amount of time, then there should always be a failsafe to just kick them from the session to prevent everyone from getting stuck in infinite loading. Once everyone has confirmed they're ready, the authority can send a final game start message. If you want to get real exact, you can even specify a future timestamp so that everyone starts the game at exactly the same time. Listening to that, you might be thinking, wait, what happens if the game start message is dropped, and so on. Like I mentioned before, I prefer to send these messages with TCP. So there's a point where you just have to accept that the other player probably got the message. This is called the two generals problem.
It goes like this. Picture a valley. In the middle of the valley is a heavily fortified castle, and on the edges of the valley are two armies. The generals of those armies know that the only way they can win a battle and overwhelm the castle is if they both attack at the same time. This problem is unsolvable.
The third problem, latency, is the real beast, and the most complicated to deal with. The more common lingo used around it is ping, which is the time it takes for a message to round trip from a client to the server and back to the client. I can add that feature to connections so that I can easily measure that. Since I'm running this all locally right now, the main thing impacting my ping is the amount of time between network thread iterations on both the server and client. Just like with packet drop, I can use Clumsy to add latency to my computer artificially. Again, I'll set it to something ridiculous like 150 milliseconds. Since this impacts the send for both the client and the server, I'll see my ping jump up to 300. Returning to the character controller, you can probably notice that despite lerping between positions, it's still stuttering around. This is because of the reduced send rate I made earlier. While the authority will send a new position each fixed update, multiple of the updates will be sent together in a single packet. This means when the client executes Q, all of those position updates will be applied at once. Instead, we want these updates to be staggered, one per fixed update, just like how it's run on the authority. To do this, I need to separate messages into ticks, where each tick we'd consider a singular moment of the game. I'll associate this with iterations of execute Q, which means each fixed update will be a new tick. Now, each time execute Q is run, a new message is sent to declare this connection is on a new tick, and that any messages received after that belong to that tick. I'm then going to combine the send and receive queues into what I'll call the simulation buffer. It'll track which tick others are on and assign messages to their latest ticks. Then, when execute Q is called, instead of consuming everything in the receive queue, messages will stop once the next tick is reached. Combining the lerping from earlier, we now have nice smooth motion. This is called snapshot interpolation, and I can use this to expand the network position script. Instead of just lerping between positions, which will be delayed based on the client's latency, you can predict next positions based on the difference between previous ticks. Once you receive an update, you can assume that the distance traveled in the next tick will be similar. So you can multiply the delta by the number of ticks that have passed since the last update to get a predicted position. This client-side prediction is a great way to compensate for latency, but should be used judiciously. Since the client is essentially making up values, once it receives the truth for the predicted tick, you can get some pretty ugly behavior. In the case of position synchronization, it'll overshoot its turn. To get good results, you'll want to control how aggressive your prediction is. The more common it is for velocities or deltas to change, the less reliable prediction will be. In this network position, there are 4 values that really decide its behavior. The lerp multiplier will control how quickly the object's actual position will be moved. At 1, it'll snap directly to the next position, not really lerping at all. The prediction multiplier will dictate how much influence the prediction will have on the actual position. This essentially controls how aggressive the prediction will be. The lower the value, the farther behind the client will appear, but it won't overshoot as much. And the higher the value, the closer the client will match, but it'll also have worse overshoots. Prediction easing is used to smooth between predictions. So when the player takes a turn, instead of the overshoot aggressively snapping to the next prediction, it'll ease into it with a better motion. Fine-tuning this, you can probably make it so that inaccurate predictions are hidden with animation. And finally, a max prediction to limit how many ticks ahead it can predict. Just like with any prediction, the farther in the future it's made, the less accurate it'll probably be. These values just need to be sweet spotted for whatever game you're making. If you're making a very fast game where players can't change their direction on a dime, such as a racing game, you can turn up the aggressiveness of your prediction. If players have very snappy movement, you can turn down the prediction and turn up the prediction easing. Of course, the need for prediction disappears when players' pings are low enough, so you can even have these values vary on a range based on the client's latency. This is a nice way to hide latency, but I want to take a closer look at this tick setup because it gets more complicated than it might seem. Let's say everyone is on the same tick at the same time. We can roughly achieve this by sending the authority's current tick to new clients, along with a timestamp of when it was sent. Since fixed update is called 50 times per second, the new client can then divide the transit time by 20 milliseconds to get its initial tick. When anyone sends messages, there will always be latency that makes it so whatever is being received will be several ticks behind. I refer to the tick on your game as the local tick. Any RPCs you send will be assigned to the current local tick, and RPCs currently being run will belong to the present tick, and will increment so long as there are new RPCs to consume. I want to make it clear that you shouldn't think of this tick as the past, and you should instead think of anything assigned to the local tick as existing in the future. This is because any local instance doesn't know the reality of the simulation until it's received updates from every other source in the session. For example, if I block on tick 13, but you've only received up to tick 10 from me, then you'll think you can attack me since I don't look like I'm blocking on your instance. Do you still get to hit me even though I saw myself blocking, or will your attack have to be negated even though you saw it land? Anything sent from the local tick represents an incomplete reality. The only thing that can absolutely be treated as truth at this point is your input. No matter what, on tick 13, I definitely pressed block and you definitely pressed attack. So instead of immediately running our inputs locally, I'll move the action logic into an RPC that's set to run locally. When this is called, it'll both be sent to the other player and be added to the receive queue. Then I'll add a rule that RPCs will only be consumable from complete ticks. This means that all the messages from all the other players, in this case just you, have to be received. That way we both see me block and you attack at the same time. This is called lockstep. There are 2 issues with this. The first is that this will increase perceived latency. While your individual connection may be really fast, the next tick being executed is reliant on everyone in the game, meaning the person with the worst ping will slow everyone else down with them. The second problem is that by not running input immediately on the local instance, I've introduced input delay, which is also dependent on the worsened perceived latency. Because of this, lockstep is a pretty niche approach, only really used for 1v1 peer-to-peer games like RTSs. I still think it's useful to know though, because I can build off of it to make the cool kid on the block rollback netcode. Rollback gets its name from its key feature, resimulation. Just like before, I'll have input execution delayed. However, instead of waiting for everyone to run the next present tick, I can keep it a fixed distance from the local tick, which will depend on the player's own latency. This means that there will still be some input delay to compensate for latency, but it won't be prone to constant lag spikes. As the present tick is being executed, each RPC will be placed in a stack, which I call the past. With this setup, one player's tick could have been not delivered yet. So when it does eventually arrive, it'll be older than whatever the present tick is now. This will trigger a resimulation, where all the previous RPCs will be popped from the past and re-queued into the receive queue, along with the new RPCs that were just delivered. Then, during the next execute queue, all of these old RPCs and the new ones will be run in one go, including what was supposed to be the next present tick. With this, I also need a way to revert game state to previous ticks. So I'll make a simulated class which maintains a circular buffer of whatever value type you give it, and maps indices to ticks. Then when a resimulation happens, getting or setting that property will use the value from that tick, and not whatever the most recent value was. While rollback has generally become a pretty standard system, you'll want to check the docs on the framework you're using, because some have it and some don't. While rollback is very powerful, it's also very expensive. In memory, you'll be storing multiple full game states. While my solution isn't exactly ideal since it's prone to memory fragmentation, other implementations I've seen use a massive struct for each tick that's compressed in memory at runtime. This amount of memory usage can cause issues if you're networking too much state. Rollback is also expensive for performance, since you'll regularly be running multiple iterations of your game logic at once. My hot take is that unless you're making a competitive game, you probably don't need either rollback or lockstep, and can easily suffice with just simple snapshot interpolation. The last technique I'll mention for dealing with latency is shared authority. This is especially powerful for co-op games, and especially dangerous for competitive ones. The idea is that instead of having a single authority that has to verify everyone's inputs and do all the heavy lifting, you can distribute this responsibility across all of the players. For example, with a singular authority, if a client wants to move, they'll have to send their input to the authority will verify and apply it, then send a state update back telling the player where their new position is. So that this doesn't produce god-awful input delay, you'll also do client-side prediction, which in this case would just mean applying the input locally, then re-simulating once you get the updates back from the server. Instead of doing all that, players can be given direct authority over their characters, which does open the game up to cheating, but I don't think anyone is going to be salty if their friend adds flying to lethal company. This is especially useful for making smooth physics simulations. If players bump into a rigid body that's being simulated by someone else, it'll look really bad as the object clips into them. Instead, players can have an area of influence around them. When a rigid body enters a player's area, the main authority can give the object to that player, and now they're the ones responsible for simulating it. Which means when they bump into it, you'll get a fast, local physics simulation instead of a slow remote one. Shared authority is used in more places than you might think. If you were playing Helldivers 2 early on in the game's release, you'll remember the constant full lobby crashes. One time when that happened to me and my friend, I noticed some of the bugs froze in place, which was what I was expecting, but some were still active and attacking. This was because Helldivers distributes the authority of its enemy AI across the players in the lobby. The bugs I saw still moving were the ones my instance was responsible for. The distribution of enemies is based on how powerful each player's computer is, so in this case, shared authority was used like a load balancer. The other way I like to use this is for object spawning, or rather as a workaround to avoid it. Let's say a client wants to shoot a bullet. Well, this bullet should be a network object, so it'll need to be spawned. But I still prefer to keep spawning privileges to the main session authority, so they'll have to send a request to get that bullet spawned, which puts us back at the same input delay problem from before. To do client-side prediction with spawning, I'll have to create a dummy object, simulate it, and then hot swap it with the actual network object once it's received. That's a massive pain, and I want to never have to do this. Instead, I'll have the authority pre-spawn a pool of bullets, and give them to the player to control. Then, when the player wants to shoot a bullet, they have full authority to enable and disable the bullets they've been given. Unlike normal object pools which only add new objects as needed, I'll set a threshold of minimum bullets in the pool based on how quickly they're shot, to send a request to the authority to spawn more bullets. That way, the client will always have more bullets than it needs to prevent any input delay. When using shared authority, I find it best to keep one central session authority, just because it's very convenient to have a singular source of truth, for things like manager state and for assigning object authority to start. The end-all be-all solution for all three of these problems is comically the simplest one. Just don't let players play. If you measure that someone has too much lag, kick them. Now that you have that threshold, you can limit your testing to the amount of lag or packet drop or throttling just below that. If the game is playable in those conditions, then it's good enough. It is important to be disciplined in this though. It can be tempting to lower the threshold to wherever the game just about starts feeling muddy, instead of improving the game's netcode. But be aware that having a threshold inevitably cuts off some portion of players from your game, and the lower it is, the more players you're losing. I've covered pretty much all of the individual techniques you might need to make a multiplayer game. Up until this point, I've been running everything locally using a single server program. But of course, in production we need much more than that. So how do we go from a single server to multiple? Depending on the framework you use, you might have hosted servers already available to you, in which case this part of the video probably won't be very important for you. For options where you have to run them yourselves, there are also plenty of services that will handle the plumbing for you. For a business, paying for one of these services versus the salary of a full-time backend dev to maintain your own system is kind of a no-brainer. But for an indie dev whose limitation is money and not time, the question is, at what point do the fees of running a smaller architecture myself surpass the fees of paying for one of these services? Which can absolutely happen. In the case of something like GameLift, it's provided by Amazon, so its pricing will pretty much just be an aggregate of the individual AWS services it's made of. So building the same thing yourself will probably end up costing the same amount or more, since you don't have the benefit of having an entire dev team dedicated to making your system as efficient as possible. But even beyond that, there are a bunch of open source projects that give you frameworks you can deploy on cloud services to take care of a lot of the process for you. And you should definitely look into the Steamworks SDK. The amount of cloud services Steam provides is honestly insane. You really aren't at any shortage of options, which can definitely induce choice fatigue. My general observation is that whatever you pick, it'll be able to handle a player base of, at a minimum, a decently successful indie game. So just go with something that seems sensible, because having to scale up your architecture because you have too many users is really just a symptom of success. A lot of the backend part of a game is honestly pretty similar to any sort of SaaS backend. Two great resources for AWS in particular are Be a Better Dev for higher level architecture to see how parts of AWS are used together, and Tiny Technical Tutorials to see how to actually implement each of those components. I'd recommend watching one of Better Dev's real game backend videos, and then look up the Tiny Tutorial videos for each of the components used. I'm personally most interested in the parts that are more particular to games, which would be matchmaking and game server fleets. Unlike the previous parts, I can't exactly battle test anything I make, since that would require a successful game with a healthy player base, or a very sophisticated simulation system that I'm not going to bother with. So most of this I'll be basing off of architectures I found in my own research. Starting with matchmaking, its fundamental goal is to give clients the arguments they need to make their connection. Minimally, the server IP and port numbers. The easiest version of this is a simple session finder. I'm not doing any sort of crazy state synchronization with this, so I can just use HTTP serializing JSON objects. In a relay service, hosts can request new relay servers be spun up, and clients can request by session ID and app ID. Then the service will respond with the connection arguments the client needs to connect to the relay. To host the service, you can put it on a microservice that accesses session data through a database queries, which are written to by the server fleet to update info about the individual servers running. But I want to start as simple as possible and build up to a more complicated system, so I'm just going to shove everything into a single EC2 instance. I'll make the Session Finder API work on a separate task, and run a relay manager which will start and stop relay connections. I could set up a whole CI/CD pipeline to get this onto the instance, but I'm not going to bother with that and just SCP the build files onto it. I'll register a domain and point it at my instance's IP, and then use Nginx and Let's Encrypt to add HTTPS, and to route requests made to the matchmaking service to the specific endpoint I have the API listening to. This is probably the most bare-bones setup I could have. I can have around 20 relays running at the same time on the cheapest server before it really starts chugging, which I'm perfectly fine with. Putting everything on a single server like this is called a monolith. I use this for game jams and making games I only play with friends, where I don't expect there to ever be a substantial player base. Ignoring what I said earlier, if you were going to use peer-to-peer, you can drop the relays and instead have hosts be the server. When a host wants to create a new session, they start a server connection. Then, when a client wants to connect, it'll send the app and session IDs to say who they want to connect to, along with their own IP and port number. The server will send the endpoints for each of them to the other, and then they'll start sending messages. The first time this happens, the messages will be ignored by the player's NAT, because it sees it as suspicious inbound traffic, but the second time it'll be accepted because it's seen as the response to the first message that was sent, allowing the host and the client to make a connection. This is called NAT punch-through. As the session plays out, the host will report changes to the server, which will impact whether or not clients can request the host's info. And finally, when the session ends, the server will drop the host data. Host will also regularly ping the server to let it know it's still active, and if the server hasn't received a ping in a while, it can assume they shut down unexpectedly and can drop the associated session. This is just simple session searching, but what about an actual matchmaking queue? When players request to be added to the queue, they'll have a ticket composed for them, which will have a bunch of data in it. The other players in their party, their rank, their region, a toxicity score, whatever you need. The most important is a timestamp for when their ticket was submitted, and a lifetime for when the ticket should expire. The player isn't going to get put in a match immediately, so instead the response will contain an ID for the ticket they were assigned so they can request the result of the ticket, and a time estimation for how long their ticket should take to resolve. That way you can show a timer for how long the player should expect to wait. If you have a party service that players use to connect to each other before actually entering a game, you might be able to send requests through the service, or you might have the party host send the request and use the service as a relay. You can build tickets in a microservice, which can handle a lot of the simple checks like if this player already has an active ticket, and compile all the data from the database, and then send them to a dedicated matchmaking server, which will handle combining tickets to make matches, which will then be sent to the server fleet. To actually match tickets, the simplest way is to just pull from the ticket queue until you have a complete match. Tickets will be sorted based on age. That way players who have been waiting for the longest get priority. The main constraint is that party sizes need to fit such that they combine to the game's team size. I just made it so that the first set of tickets that work is used for the match for simplicity, but really this is a combinatorics problem, where you're trying to solve for the combination of tickets that will resolve both the largest number of tickets and the oldest. If a complete match couldn't be made, then the dequeued tickets get re-queued and it tries again, given a threshold where incomplete matches will just be accepted anyway. If the ticket expires, then the player will be notified, or they can just be running their own countdown knowing their ticket's lifetime, and they can restart the process, sending another matchmaking request to get another ticket. To start matchmaking based on a heuristic like rank, you need a data structure that's much easier to search through. So when queuing a new ticket, I'll also insert it into a binary search tree that's sorted by rank. Then when I try to make a match for a ticket, I'll get a view of the tree whose range expands as the ticket gets older. This works great, but good matchmaking is rarely using only a single value. For example, I want to match players who are not just at a similar rank, but who are in a similarly sized party, because a bunch of solo queuers are going to have a much worse time against a 5-stack. You might think the solution would be to find some clever way to combine rank and party size into a single number to continue using a BST, but this doesn't work. Think of rank and party size as two dimensions like x and y. Combining them into a single value is effectively the same as taking the magnitude of the two as a vector. You might not be using the exact equation, but it's logically equivalent. Doing this, a bunch of solo queue high-rank players can be matched against a low-rank 5 stack. By reducing the two, you're losing necessary information. A better option is R-trees. These use bounding boxes to separate values into multiple dimensions. Nodes have a certain capacity of children, which when it's reached, the node splits in half into a new sibling node, which will take half of its children. Then they will reevaluate their bounds to fit tightly around what they contain. To query, you give it another bounding box and it'll return the values that are inside it. This is a really efficient structure since the tree height will only increase if splits propagate all the way to the top of the tree, and since bounds are tightly fit, you won't waste time checking empty space. However, depending on how values are inserted in split, you can get overlapping bounding boxes. This means queries will waste time searching the same space in different nodes multiple times. As it turns out, as you increase the number of dimensions, the worse this problem becomes. So R-trees break down once they hit too many dimensions, which we might want in our matchmaking. Beyond rank and party size, there's region, KD, win-loss ratio, hero or class preferences, social factors like toxicity or faction standing. There's a lot you can account for, so supporting higher dimensions is pretty desirable. The best solution I was able to find was to use hierarchical navigable small worlds, which are used primarily for querying vector databases and are purpose-built to handle multiple dimensions. But in my own hubris, I wanted to see if I could make improvements to R-trees that made them able to handle higher dimensions. What I came up with was kind of a hybrid between R-trees and KD trees. When nodes split, instead of bounding tightly around their children, they subdivide their original area. When a split happens, the original node records what that split was. Then, when its parent needs to split, the child with the largest recorded split is used for its subdivision. That record is then taken from the child and given to the parent, which allows the split to trickle up the tree as it grows. This is essentially storing the branches that a binary tree would hold in its structure to avoid overlaps, but also still using R-tree splitting mechanism that allows it to stay very shallow. The trade-off, other than extra memory usage, being now that bounding boxes aren't tightly fit, empty areas will always be covered. The closest thing to this I was able to find are R+ trees, so I have no idea if what I made is actually useful or not. An important part of matchmaking is getting to a critical mass. If there's no one else online, a player isn't going to wait for someone, they're going to go play something else. Wait times are proportional to the number of players playing, and the number of people playing depends on the wait time. There's a point of critical mass when the size of the player base is large enough such that the players will keep playing because there are enough other players for them to match with. If a game doesn't reach critical mass early on, it usually dies. You can fake critical mass with bots, which is especially useful for onboarding. Since new players aren't going to have a history of stats the matchmaker can use, it'll be pretty difficult to place them in a match with any other players besides other newbies. Plus, it'll give them much more leeway to learn the game before going into a match and getting steamrolled by actual people. Or, more creatively, you can record user input and replay it as a fake opponent for someone else's match. The viability of this is definitely dependent on the game though. Once a match is formed, a server needs to be assigned to hosting it. This can be handled by one big server manager which is in charge of starting and stopping sessions, or you can distribute this among a bunch of server managers, one for each region you want to host in. Since the matchmaker will assign the region, it'll know which manager to send the match to. Each of these server managers can even be used as ping targets for players. The manager that has the lowest ping to the player is what region they would say they belong to. Then once the manager starts the session, to get the connection args to the player, it can do one of three things. It can use the party service to notify players, assuming your game has a party service, or players can use their matchmaking ticket ID they were given in response to their matchmaking request to repeatedly pull a microservice. The manager will put the connection args in a database, which the microservice will read from to see if the player's tickets have been completed. Or players can connect to an event bus where they'll wait for the manager to send the args through the bus to them. You either have the client send a request, in which case you need some sort of temporary storage to hold the data until the request is received, or you send it to the clients directly, in which case you need to maintain an open line to the client until that data is ready. Now to actually run these sessions, again, scaling up can be done in gradations. You can essentially make each of these server managers into one of those monoliths from earlier, which would work if you're using peer-to-peer like before, but still want sophisticated matchmaking, or if the game is lightweight enough or turn-based such that a single server could handle everything for each region. Even with a heavier game, if a region has particularly low player counts, you might be able to run a couple servers on the manager in containers without needing to start up extra resources. But I'll stop dragging my feet. How do you scale real-time game servers? The server manager will spin up and stop Docker containers, which I'm going to assume you know what that is for brevity, which run on a server fleet given to it. These servers will start up as they're needed and shut down when they're not. In AWS, this would look like using ECS with an EC2 ASG. Doesn't that sound horrible? An auto-scaling group will handle the starting up and shutting down of EC2 servers based on utilization metrics. To me, it makes most sense to use memory. This is because containers will be allocated a fixed amount of memory when they're spun up, so this gives you a reliably exact number of containers that will run on each server. This ASG is then given to a container service, which will use it as its hardware to run containers on. Then the server manager will talk to the service to start and stop those containers, which AWS calls tasks, using the AWS SDK. The manager will have a set of RUDP sockets it'll have servers connected to, which it'll give the endpoint for along with its connection args through environment variables. You can use this connection for whatever, but the most important thing I want to use it for is to tell the server manager the session ended. So the manager can tell the container service to end the task and do whatever other cleanup has to be done, such as removing the match data from the database and updating player career stats. This is using AWS's system just because I find its SDK pretty straightforward, but the more standard version of this is Kubernetes using Agones, which is an extension for Kubernetes made specifically for running game server fleets. I could probably spend another month going through Kubernetes though, so I'm just going to leave it at that. The final piece I'll add is that with all of this, there are a lot of endpoints the client could potentially hit. I don't want to have to push updates to the game client anytime I change one of these, so I'll reuse that domain I got to just return a JSON object with all of those endpoints. Now if they change, which might happen if I take down one of them for maintenance for example, I just update the JSON file and clients will only really need to know that one domain. For whatever game you're making, a general sentiment I keep finding is to go with the simplest architecture you can. It'll make it easier to develop for and cheaper to run. If your player base grows to where you need to start scaling up, temporarily pay for more powerful servers while you experiment with more distributed architecture. You honestly might find that scaling vertically like this ends up being cheaper than scaling horizontally, and effective enough that you don't need to scale horizontally at all. Being able to support 1 million players only matters if you actually have 1 million players. If you have a casual turn-based game, use a monolith session finder with peer-to-peer. If you have a competitive turn-based game, have a single matchmaking server and a game server that runs everything. Have a small to medium-sized real-time co-op game, have a session finder server that doubles as a server manager with containerized relay servers. Have a big co-op game, use a session finder microservice that queries a database of sessions updated by regional server managers running relays. Have a full-on live service, use a matchmaking ticket building microservice that feeds a matchmaking server which sends matches to regional server managers running containerized game servers. Don't want to think about any of this? Pay someone else to handle it for you. Just making games for your friends, put it all in a monolith, or to be honest, just use one of those services because they're free at that scale. Beyond the scale of your game, creating the backend should also be considered part of the game itself that contributes to the game design. Maybe you want to do social network-based matchmaking, where players who have played against or with each other previously are more likely to be matched again, so you can make something like the Nemesis system but with real people.
So think about the journey from stranger to acquaintance to friend and how you can enable that. Whenever I have a match, whenever I compete against you, it is a story, right? But the next time we match up, you can say, hey, do you know you played this person on Friday? Oh yeah, you beat them, but they were really favored rockets, or their aim was really good. And you can start telling the story, you can start building on that. And as you save this relationship up, there's more data there to do storytelling.
Or have players contribute to an ongoing war campaign. Or have separate lobbies occasionally merge together to do a raid boss fight before splitting off again. Whatever part of the game's backend that are standard, you should use out-of-the-box solutions, whether that's paid-for services or open-source projects. And the parts that make your game unique, you should put more effort into handcrafting. At least to a degree. Nobody should be remaking Kubernetes. The important thing is that your game's backend is what drives the meta-narrative of your game. That could be individually per player through their experience climbing ranks, or community-wide as big events happen. And finally, it is very important that the game works without a backend. This goes beyond just game preservation. Making it so your game can be played offline single player is like hedging your bets against reaching critical mass. Most games fail. If your game doesn't reach the player base needed or isn't profitable enough to justify maintaining a multiplayer backend, you should shut it down or scale it back. Unless you have funding from another source you're willing to burn, or you're operating in a scale most services would give to you for free. When that inevitably happens, having an offline playable mode will allow some residual community to maintain itself through speedruns, challenge modes, modding, and fringe Discord servers, which is extremely valuable. Since in the current gaming landscape, having a community of players you have goodwill with, however small, is one of the greatest things you can leverage for your next game. One video from Unity I watched had a particular quote that stuck with me.
All started talking about cloud a really long time ago. Nobody really knew what it was. It was largely an engineering space. People understood very little about it. And over time, you develop tools to shortcut it, to string different services together to make it very reliable, very scalable and dependable. And I think that's where we're going with game scaling. I think that's what's going to happen. It's going to be more pluggable. It's going to be very templated and very easy to succeed. That infrastructure is going to be standardized. And I see that happening really soon.
This was in 2022, and I'd say this was largely correct. The trend in multiplayer frameworks isn't just to offer a programming interface, but to also provide services to run your game on top of so that the only thing you really need to think about is the game itself. Slowly but surely, multiplayer is becoming more and more of a solved problem. So much so, I'd say part 1 and 3 of this video will probably be useless to most of you. Despite the title, you've probably realized that this isn't really everything multiplayer. I didn't mention determinism, only briefly touched on cheating here and there, didn't show anything for long-running games like MMOs, and didn't really say anything about making your backend secure. While that might be disappointing to some, the basically infinite depth every problem space in programming has is what I enjoy about it so much. Below in the description, I've left a ton of resources you can use to expand off this video into whatever topic you need, so hopefully you'll be able to pick your battles better than I did. When I first started this project, I honestly had no idea whether or not I'd be able to finish it. In a lot of ways, it's still not done. But at this point right now, it feels like I've reached the top of a mountain. And after listening to me go on for an hour, I bet it feels that way for you too. After all this, I think it's about time we actually make a game. Good luck, and thank you for watching.